Hey everyone, welcome back. In today's video, we're going to tackle a highly relevant topic for Python interviews practical questions on multiprocessing. Python's multiprocessing module is a powerful tool for running multiple processes in parallel, making it ideal for CPU bound tasks and breaking through the limitations of the global interpreter lock kill. Whether you're preparing for an interview or just looking to sharpen your skills, we'll walk through some practical real world scenarios to help you master multiprocessing. Let's jump in and see how it works. Definition: multiprocessing in Python is a great way to run multiple processes at the same time, with each process having its own separate memory space. Unlike threads, which share the same memory, processes are completely independent, making multiprocessing perfect for tasks that require a lot of computing power, like heavy data processing or complex calculations. Since each process runs separately, the Python global interpreter lock-kill doesn't limit their execution, which means you can achieve true parallelism running things side by side without interference. Python's multiprocessing module makes it easy to take advantage of this, allowing you to use multiple processors and cores to boost performance, especially when you're working on CPU-intensive tasks that would normally slow down with multi-threading. Key benefits. One of the biggest advantages of multiprocessing is parallelism. Unlike multithreading, where tasks may be delayed due to the global interpreter lock-kill, multiprocessing allows for true parallel execution across multiple CPU cores. So tasks can run simultaneously without waiting on each other. Another benefit is isolation. Each process runs independently with its own memory space, which means you don't have to worry about issues like race conditions that are common in multithreading. This makes multiprocessing a perfect choice for CPU-bound tasks, where you're dealing with heavy computations or data processing that can really benefit from spreading the load across multiple processors. It's ideal when you need to maximize your system's processing power. Python's multiprocessing module provides. Python's multiprocessing module gives you everything you need to manage processes effectively. First, there's the process class, which allows you to create and manage separate processes. Each process runs independently, which is great for tasks that need to be isolated. Then you have the pool, which lets you manage a pool of worker processes. This is super handy when you want to run a bunch of tasks in parallel without manually creating and managing each process. For communication between processes, you can use a queue, which ensures data is passed safely between them without conflicts. And if you have shared resources like a file or data, lock helps manage access to make sure only one process is using it at a time, preventing any data corruption or race conditions. It's a powerful set of tools to get your tasks running smoothly in parallel. Now that we've got a solid understanding of the basics, let's dive into some practical examples to see multiprocessing in action. We'll walk through how to create processes, use pools for parallel tasks, and safely communicate between processes. These examples will show you how to make the most of Python's multiprocessing module, especially for handling CPU-bound tasks efficiently. Let's get started. 1. Basic process creation. Question: write a Python program to create two processes that print numbers from 1 to 5. In this example, we use Python's multiprocessing module to run two independent processes in parallel. Unlike threads, which share the same memory space, processes have their own memory space, making multiprocessing an effective way to achieve true parallelism. This is especially useful for CPU-bound tasks that require significant processing power, as processes can run on different CPU cores concurrently. The print underscore numbers function, which prints numbers 1 to 5 with a 1 second delay between each number, is executed by both processes. Two processes, process 1 and process 2, are created using multiprocess.process with the target print underscore numbers argument specifying that both processes will execute this function. When the processes are started using start, they run concurrently, meaning both processes execute the print underscore numbers function at the same time. Each process operates in its own memory space, so their execution is independent and the output can interleave, reflecting the parallel nature of their execution. The join method is used to ensure the main program waits for both processes to complete before continuing. By calling process1.join and process2.join, the main program is blocked until both processes finish executing. After both processes are done, the final message both processes have finished execution is printed, indicating that all parallel tasks have completed. 2. Using multiprocessing.pool. Question: write a Python program that uses multiprocessing.pool to calculate the squares of numbers in parallel. In this example, we utilize Python's multiprocessing.pool to distribute a computational task across multiple processes. As mentioned in the earlier response, processes in Python run in separate memory spaces, enabling true parallelism. This is particularly useful for CPU-bound tasks like calculating the square of numbers, which can benefit from being distributed across multiple CPU cores. The square function is a simple function that computes the square of a number. In this case, we use the pool class to create a pool of 3 worker processes, meaning up to 3 processes can run simultaneously. The pool.map method is then used to apply the square function to each element in the numbers list. This method divides the list of numbers among the available processes, allowing the computation to occur in parallel. Each process handles a portion of the list, calculates the square of the numbers it is assigned, and returns the results. By using pool.map, the task of squaring the numbers is distributed efficiently across the available processes. Once all processes complete their work, the results are collected and printed. This parallel approach significantly improves performance for CPU-bound tasks by leveraging multiple CPU cores as compared to running the function sequentially. The pool method is an easy and effective way to parallelize tasks, especially when you need to apply the same function to a large dataset in a concurrent manner. This approach is ideal for parallelizing CPU-intensive tasks because each process runs in isolation, without the limitations of Python's global interpreter log-GIL that affect threading. It allows for true parallel execution utilizing multiple CPU cores and provides a robust method for handling tasks that require significant computation or need to be processed simultaneously. 3. Shared memory with value and array. Question: write a Python program to demonstrate shared memory using multiprocessing.value and multiprocessing.array. In this example, we use Python's multiprocessing.value and multiprocessing.array to create shared memory objects that multiple processes can safely access and modify concurrently. These shared memory objects allow different processes to communicate and share data, ensuring that each process has access to the same value or array, instead of operating in isolated memory spaces. This example builds on the concepts explained in the earlier response about process parallelism and synchronization. The increment function is executed by multiple processes and is responsible for updating the shared value and array. The value object holds a single integer and the array object holds a list of integers. Since multiple processes are accessing the same data, we use get underscore lock to ensure that only one process modifies the shared memory at a time. This locking mechanism prevents race conditions where processes might try to update the same value simultaneously, which could lead to inconsistent or incorrect results. Each process acquires a lock before incrementing the shared value or modifying the shared array. This ensures that only one process has access to the shared resource at any given time, maintaining data integrity. After the process increments the shared value by 1 and updates each element in the array, the lock is released, allowing other processes to proceed. This pattern is crucial in multi-process programming as it guarantees that updates tasks to shared data happen in a synchronized, orderly fashion. At the end of the program, after all processes have completed their work, the main thread outputs the final value of the shared value and array. Since 3 processes each incremented the shared value by 1, the final value of shared underscore value is 3. Similarly, each element in the shared underscore array has been incremented by 3 as each process incremented each element by 1. This demonstrates how processes can work together to modify shared data with the use of locks, ensuring that these modifications are safe and synchronized. 4. Process communication using queue. Question: write a Python program where one process produces data and another process consumes it using multiprocessing.queue. In this example, we implement the classic producer-consumer problem using Python's multiprocessing module and a multiprocessing.query for interprocess communication. As explained in the earlier response, the producer-consumer pattern involves one process generating data producer and another process, another process processing the data consumer. In this scenario, the producer generates 5 items numbers 0 to 4 and places them into the queue, while the consumer continuously retrieves and processes these items from the queue. The multiprocessing.query serves as a thread-safe communication channel between the two processes. The producer process runs the producer function where it generates items each one into the queue using queue.put. After each item is produced, there is a 1 second delay to simulate real-world production time. The consumer process runs the consumer function, where it retrieves items from the queue using queue.get. The consumer continues consuming items until it encounters a none value which signals that the producer has finished producing and the consumer should shoot. The main process starts by creating and starting the producer and consumer processes using multiprocessing.process. After the producer finishes generating items, the main process waits for the producer to finish by calling join on the producer process. Then it places a none value in the queue to signal the consumer to stop. Finally, the main process waits for the consumer process to finish by calling join on the consumer process. This approach efficiently synchronizes the production and consumption of items between processes using a queue to manage shared data. The non-sentinel value allows for a clean and controlled shutdown of the consumer process, ensuring that both processes terminate properly once their tasks are completed. By using multiprocessing, we achieve parallelism where the producer and consumer can run concurrently, improving efficiency in scenarios where production and consumption can happen simultaneously. 5. Using logs to prevent race conditions. Question: write a Python program where multiple processes update a shared counter. Use a log to prevent race conditions. In this example, we utilize Python's multiprocessing.value and multiprocessing.log to safely share and modify a single counter variable across multiple processes. As explained in the earlier response, processes run independently and have their own memory space. However, using multiprocessing value, we can create a shared memory object, in this case an integer counter that all processes can access and modify. The lock ensures that only one process can modify the shared counter at a time, preventing race conditions where multiple processes try to update the value simultaneously, which could lead to inconsistent results. The increment underscore counter function, which is executed by each process, increments the shared counter 100,000 times. The with lock block ensures that only one process at a time is allowed to increment the counter, enforcing mutual exclusion. This ensures that while one process is updating the shared variable, others must wait for their turn, preventing any conflicts during the modification of the shared resource. In the main block of the code, we create 4 processes, each tasked with executing increment underscore counter function. Each process will increment the shared counter 100,000 times, and since the lock is used, all increments are applied correctly. After starting all the processes, we use join to wait for each process to complete before printing the final value of the shared counter. Since each process increments the counter by 100,000, the final value should be 400,000, demonstrating that shared resources can be safely modified by multiple processes using a lock. This approach ensures thread safety when working with shared resources in a multi-process environment, providing a robust way to handle shared memory in Python's multiprocess module. By using a lock, we prevent issues such as race conditions, which are common when multiple processes or threads access shared data without proper synchronization. 6. Multiprocessing with process class and arguments. Question: write a Python program that demonstrates how to pass multiple arguments to a process using the process class. In this example, we demonstrate how to use Python's multiprocessing module to create and run a process that takes multiple arguments. The multiply function accepts 2 arguments, multiplies them, and prints the result. The process is created by passing this function as the target and the arguments 5, 10 using the args parameter. This example builds upon the explanation from the earlier response, which detailed how multiprocessing enables parallel execution of tasks in separate processes. The key feature here is the ability to pass arguments to a function executed by a new process. The args parameter allows us to provide the arguments for the multiply function, enabling the function to multiply 5 and 10. This parallelization allows the function to run independently of the main program. The process is started using the process.start method, which triggers the execution of the multiply function in a separate memory space, enabling true parallelism. Once the process is started, the process.join method is used to synchronize the main program with the process. This ensures that the main program waits for the process to complete before proceeding. Without this synchronization, the program could finish its execution without waiting for the process to finish its task, which would lead to incomplete results. After the process completes, a final message is printed to indicate that the task has finished. This demonstrates how the multiprocessing module can be used to pass arguments to target functions, allowing processes to handle tasks with varying inputs. This method is crucial when working with tasks that need to run in parallel, especially in scenarios where the functions require specific arguments for their execution. By using multiprocessing, we enable better resource utilization and faster processing times for tasks that can be executed concurrently. 7. Using multiprocessing.pipe for two-way communication. Question: write a Python program where two processes communicate with each other using multiprocessing.pipe. In this example, we utilize Python's multiprocessing.pipe to facilitate inter-process communication between a sender and a receiver process. As explained in the earlier response, pipe creates two connection objects, parent underscore con and child underscore con, which represent the two ends of the pipe. These connections allow data to flow between two processes. The sender process sends data through one end, the child connection, and the receiver process retrieves the data from the other end, the parent connection. The sender function loops through a range of 5, sending messages like message 0, message 1, and so on through the child end of the pipe using con.send. After sending all the messages, the connection is closed with con.close, indicating that no more messages will be sent. On the other hand, the receiver function continuously reads messages using con.read. As long as there are messages, the receiver prints each message. The loop continues until a none value is received, signaling the end of communication, and the receiver then stops. The main program coordinates the execution of both processes. It creates the sender and receiver processes and starts them using process.start. After the sender completes its task, the main program sends none through the pipe to inform the receiver that there are no more messages to process. The join method is used to ensure that both processes complete before the program proceeds further. The final output, communication through pipe P finished, confirms that the inter-process communication has concluded. This implementation showcases how multiprocessing.pipe allows two processes to communicate efficiently by passing messages through a pipe. By using the pipe, we enable one process to send data and the other to receive it in real time. This mechanism is crucial for parallel tasks that need to exchange data or synchronize their actions. The use of none as a sentinel value ensures clean termination of the receiver process, preventing it from hanging indefinitely. This method is ideal for simple two-way communication between processes. 8. Process pool and async result. Question: write a Python program that uses a process pool to calculate the factorial of numbers asynchronously. In this example, we use Python's multiprocessing.pool to distribute the task of calculating factorials across multiple processes, allowing for parallel execution. This builds on the earlier explanation of how the pool object can manage a group of worker processes to handle multiple of work. Here we calculate the factorials of numbers ranging from 5 to 10, leveraging the apply underscore async method to run these calculations in parallel. The factorial function calculates the factorial of a given number using a loop. Instead of calculating the factorial of each number sequentially, we use pool processes 3 to create a pool of 3 processes. The pool enables us to distribute the work across 3 worker processes, improving efficiency by allowing the calculations to happen in parallel. Using the apply underscore async method, each factorial computation is scheduled to run independently on one of the worker processes. This method returns an async result object for each task, which can be used later to retrieve the result. After scheduling the tasks, we use a loop to retrieve the results by calling get on each async result object. The get method blocks until the result is ready, ensuring that the main program waits for the computation to finish before printing the results. This method allows us to handle tasks asynchronously, making it possible to run multiple independent calculations in parallel, significantly speeding up the process. By using multiprocessing.pool and apply underscore async, This approach efficiently distributes CPU bound tasks across multiple processes, making it well suited for situations where independent calculations can be performed in parallel. The use of pool allows us to control the number of concurrent processes, ensuring optimal utilization of system resources while avoiding the overhead of manually managing process creation and synchronization. That wraps up our deep dive into Python's multiprocessing. I hope you now have a clearer understanding of how multiprocessing works and how you can apply it in real world scenarios. It's a powerful tool for optimizing performance when working with CPU bound tasks. If you found this video helpful, make sure to like and share it with others who might benefit. Don't forget to subscribe for more Python interview prep and practical coding tips. Thanks for watching, and I see you in the next one.